Okay. Okay, in previous classes we talked about elastic behavior of materials, linear elasticity, viscoelasticity, ferroelasticity, and he was talking about reversible mode of deformation in materials that can be time dependent, time independent, that we discussed. Today we start talking about irreversible deformations in materials that very easily can be seen in metallic materials, also in polymers, that when we apply load to such materials, we deform them, and this deforming at low loads is elastic. After critical stress, we call it yield stress, materials start to deform elastically. It means after releasing or unloading the load, the deformation will not come back to the original. Yeah, that is, we know it as a plastic deformation, and we want to see it in metallic materials today. What is the reason? And all details of the from microstructural point of view, why we have plastic deformation and different, we see it in different aspects. Also, we have this plastic deformation, or in polymers, we call it viscoplastic. Even we can see some plastic deformation in ceramic materials. That these two, or a little more about metallic materials as a continuation of this class, will come in next classes after control one. So let's talk about plastic deformation in metallic materials today. So we are focused on metallic materials. You already know well metallic materials that are crystals. The majority are BCC, FCC, and HCP crystals. And in this slide, I already explained it in first class, I think, about if we apply load on a magnesium in a single crystal magnesium, and in this single crystal magnesium, if we have a basal plane with this angle to the force or direction of the force we are applying, we will see such a deformation, which is a plastic deformation. It means at the beginning we have a little elasticity, but very fast we reach to a point. If we continue applying load, we will have plastic deformation, and when we unload, we will see a permanent deformation or tensile strain on the sample. Microscopically, also, when you see this sample, on the surface of the sample, you see some such a lines, we call it slip lines, and the shape of the sample will be like this. It means some part of the sample moved or slipped on the other part of the sample, and this is the plastic deformation. Yeah. So today, from the now till the end of the class, we have to answer several questions from this just very simple test. First is why basal plane is important here. For example, in magnesium, which is HCP, basal plane, which is this closed packed crystal structure, crystal plane, why, if the formation want to happen, why this plane is more easy for deformation than other planes? This is one simple question. Another is why, if we align this sample with this angle 45 degrees to the direction of the applying load, why we have more easy deformation than other directions. Yeah, this is another question that is common, and you want to explain it. Another question is, or the other question is this: when we reach to the point that we have the formation, why we have a plateau here, it means, okay, it's plateau because the deformation has started and this part is moving on the other part, and there's no need to increase the stress that we apply. We reach to that critical stress. But why here again start to move up? Yeah, these questions we want to go and answer. Okay, first, just as a definition, as something that you have to be familiar with this topic, that when we talk about plasticity, how plastic deformation occurs in materials, especially metallic materials, all the time we came to these two mechanisms, slip and tuning. Yeah, in these schematics, easily you can see what is a slip and what is a tuning. Yeah, if we deform a material and we have different portion or different parts of the crystal slip on each other, it means displacement happen in just one plane like this. This mechanism is a slip. This can happen in ceramic even. For example, this is a slip plane and this part is moving on other part just in this plane. Yeah. But we have also another mechanism for plastic deformation. We call it twinning. Yeah. And this not happening just in one plane. It's happening in the volume of the material, that this fast movement of this part of the crystal make the formation of plastic deformation in material. Yeah. So we are focusing on these two mechanisms uh, that are the mechanism for plastic deformation. First, I
Teacher?
explain. Yeah.
But twin has not the same force orientation, right?
Look, for example, this just also here you can see if you are if you have a single crystal and you are applying load in this direction, if something like this happen, its mechanism is a slip. If something like this happen, it means the mechanism is twinning, it's not slip. Yeah, the mechanism is different. Now I will explain what is twinning, and later we will talk more in all class of today about the slip. Yeah, so let's briefly talk about the slip because it's twinning, because twinning is a less important mechanism for plastic deformation. But as it happened, we have to be familiar with it. Okay, so if you apply load to metal, yeah, you can activate both of these mechanisms. Yeah, but the slip is happening more frequently and more easy, so we see it more here. But in some metals, like a tin, we see this mechanism, which is twinning. Yeah, and this twinning is something like a movement of the portion of the crystal in such a way, like this. Yeah, that make a habit plan here, and you can see as a mirror here. Atoms will become like a mirror around this, and again we have it here. So this deformation happening here, by this way we call it twinning. Yeah, and we see it in some metals, and sometimes it's with sand. Let's show you these videos because um, just a moment. You're seeing these videos? Yes.
Yes. Yes.
Yeah, we just share the sound of my. Yeah. This phenomenon is called the tin cry or tin scream here. Say, yeah, it's a tin, yeah, a metal. It's a tuning deformation happens to it more easy than other metals. And when this happens, the sound is coming out. Look, you, you listen.
Yes, yes.
This is thin cry or thin scream. Okay, this deformation or plastic deformation in this metal is trimmed by this mechanism. Yeah, that happens to these metals, and other metals also can happen, but this is very famous as a thin cry. Okay, and here you can see in this table in BCC, ACP, and FCC metals that the twin planes and twin directions also that can happen, but sleep deformation in, for example, in FCC metals is happening more easily. So the mechanism of this deformation by tuning is less important for us when we talk about velocity deformation. So we can escape from this and come back to the sleep. Okay. So sleep is the most important mechanism for plastic deformation, and it's happening when we apply a shear stress. Is happening by shear stress. If there is no shear stress, we don't have plastic deformation by slip. So we have to have shear stress. It means one part of this crystal has to uh, be under the shear stress to compare with the other parts like this. And the movement of this upper part to the lower parts by a slip is plastic deformation by mechanism of slip. Yeah. So for that, we need a slip direction and a slip plane. Not necessarily in all crystal planes happen this slip deformation, because in some planes the deformation is more easy and in some no. And that is very simple. Those planes are close packed like this. um, like these planes, it means if I continue like this, it will be like this. Yeah. It means it's close packed. It cannot be more compacted than this. So this is a plane, and when we apply shear stress on this, movement of this plane on this plane is easy. So this is a slip plane. Compare it with this, yeah. For example, now in this direction, compared with previous direction, this is more difficult. Now, if you want to compare the plane, let's say just in FCC, for example, if I can draw something by mouse, yeah, just that is enough. So this is 11100. This is 111 in FCC, for example. This plane, compared with, for example, this plane, they are less compacted or less close packed. Okay, so the movement of these atoms coming from this side and come here, and this coming here, is more difficult for compared with this coming this here and this coming here. Yeah. So in all crystals, those planes are more close packed or more dense. It means the separation of the planes that are packed on each other is more, as they are more separated. So movement of the plane on each other is more easy. That we call slip plane. Yeah. More than slip plane, inside of the plane also that different directions have different density. For the direction, just compare this schematic with this. here we have one direction, here we have this direction, yeah? Just to understand the angle of this here is here, yeah? It means if you apply stress in this direction, it's more easy to move this plane than this plane is more easy than moving this plane to this plane, okay? So another thing for a slip is the slip direction. Again, is the closest path direction inside of the slip plane, yeah? So when we want to talk about slip or slip mechanism for plastic deformation, we have to talk about a slip system, which is a slip plane and a slip direction. Yeah. In different crystals in metallic materials, we have different slip systems. It means they're composed of different directions and different planes. Yeah. In FCC crystal, this is a FCC crystal, as we see here. This was a closed pack. Here you can see from up. This closed pack plane is this 1, 1, 1. What is this? Is here. You see? Yeah. This is closed pack plane, and this just this plane has 3 directions inside. One is this, another is here. Sorry, I cannot draw it like this. Here you can see just these 3 directions, yeah, for FCC crystal, and we have such a plane, 4 planes in the FCC crystal. It means if you imagine in this cubic, this is one, another instead of this corner, we can reach to this corner, this, and this is another, this corner, and other corner is other side is another, and this corner, that corner is this other side, and this is another plane. So we have 4 planes in FCC crystal, which have such a configuration is closed path, each of which has 3 directions. Yeah, here maybe I can draw it more easy. This direction, yeah, and this direction. Yeah. So also we have 3 directions. So the number of slip system we have in a FCC crystal are 12. Okay, 12 slip systems we have in FCC crystals. In body center cubic crystals like iron or tungsten, which is this, we don't have such a closed pack plane. You cannot find any plane like this closed pack. But we have a closed pack direction of 1, 1, 1, which is coming from here and passing to this part, or diagonal of this cubic is a closed pack direction. As we don't have closed pack planes in this crystal, yeah, we have to consider other planes like this plane, and this plane. They are not closed pack, but we can consider them as a slip plane, okay? And we have 3 directions for slip plane. So finally, we have 48 slip system for BCC, but none of them are closed path direction with closed path. Closed path direction there is, but not as there is no closed path plane, there's deformation or plastic deformation in BCC metals is more difficult than FCC because here this condition make it more suitable for deformation. And also for hexagonal closed path, that basal plane that already we talked about, this is a basal plane, which is similar to 1, 1, 1 plane of the FCC. is a closed pact. Inside of this closed pact, we have this direction, yeah, which is slip also, which is this, yeah. And there is another two planes that we can consider as a slip plane, and this in this direction. So finally, we have 12 slip system in HCP crystals. Yeah. So we can calculate theoretically how much shear stress is needed to move two planes on each other. Yeah. And as we was talking about magnesium, that's in this slide is calculated for magnesium. So if you want to move one plane of this plane to this plane, so you have to move it with, if the distance between these planes is this 2a, yeah, the movement will be a, so you can shear a strength that happens by this movement will be half, like this, okay? And we know the shear modulus of magnesium, so we can calculate the shear stress is needed for movement of these planes in magnesium, which is about 10,000 megapascal. Yeah, it means applying shear stress on this in this way. Yeah, theoretically, for this movement of this, for example, two planes of this crystal, you need theoretically 10,000 megapascal. Yeah, that is much more than that we see here. It's about 1 megapascal. Yeah. So just keep in mind that sleep, how it's happening by shear stress. The shear stress is needed to move two planes on each other is much more than that needed practically. Another thing that before going to talk about this discrepancy between the practical and theoretical, let's talk about the angle. Do you remember we talked about you have to put the slip plane in 45 degree, that we have maximum shear stress. And why this angle? That's coming from this Schmidt law, that if you're applying on a crystal tensile load like this, yeah, if you, this is your slip plane, if you apply load normal to this plane, it means if you put this plane here and you're applying load like this, yeah, nothing happened because you're applying tensile strength to a slip plane, and as your shear stress is zero, there is no slip there. Or if you apply this load parallel to this, it means this plane, which is a slip plane for this, is in this direction. Again, you cannot deform it by slip because you are applying parallel to the plane, and these planes cannot slip on each other. Yeah, so we must have an angle. And what is this angle? This coming from this Schmidt law that the stress we are applying, yeah, is equal to the load to this area. Okay, this is the stress you're applying. Load, for example, Newton, and this area is area. And we can relate this area with the area of your sample, which is this AN. So we define a theta, which is the angle between the plane and the direction of applying load. Yeah, this is one angle we can define. Another is this phi, which is an angle between the direction of the load and the angle of the direction of the slip inside of the crystal. Yeah, so if, and this is phi, so again we can write, instead of sigma A, we can obtain the shear stress because the shear stress happens in this direction. Okay. So we finally reach to this equation. We know it as a Schmidt's law. And by this stream flow, by these angles, easily you can calculate that when these theta and phi are 45 degrees, we have minimum resolved shear stress for a slip. It means when you're applying load, if your slip system is in with this angle, you need minimum shear stress to move these planes together, and this is 45. Okay, so this is the reason why in that previous test, the slip planes was, or basal plane of magnesium was, it has an angle of 45 degrees to the direction of the load. Okay, and you will see here, if you change these angles or this factor, the minimum will be here when theta is 45. Yeah, if you change it, you need higher tensile stress to reach to that shear stress that you need for a slip. Yeah, so this is the reason why this angle is matter and why we see these slim planes with this angle on the surface of the sample. So let's come back to this test that we want to understand the behavior of the materials for this test. So by this knowledge now we know that this part is elastic, that is the separation of the atoms that are like a spring or connected together by bonds. When we apply load, we are separating just atoms by contraction and repulsion forces between these atoms. If we release the load, they come back again in the original place, and that is elastic. But when we increase the load or tensile stress, these tensile stress depend on this angle, which is here for this case, the slip plane is in 45 degree to the direction of the tensile load. So the shear stress is minimum. So in this stress, for example, the formation of plastic deformation stopped. Like this. It means one of these planes that we have loss of these planes inside of the material. In one of them, slip can happen. Not necessarily in one, can happen in several. And when this slip happens, some uh, steps appears on the surface. So we call it a slip line, and we can see it on the surface of the sample. Okay. And there is no reason when we reach to this critical stress for further deformation, increase of the stress. It means here we have a plateau, so it must be like this, yeah? But actually it's not like this. When we reach here, the sample starts to deform, needing higher tensile strength. It means, for example, if you deform this sample, this amount of strain, if you want to continue deformation, you have to apply higher tensile stress. Okay? So what is the reason behind this? This is very simple. This is the depend how we do this test. Just we put samples between the two fixtures, grips, like this and here, and the equipment we have for doing such a test doesn't move horizontally. Yeah, just this fixture move up and pull out the sample. Okay. And here you will see when you have deformation and you are making a step here, yeah, it means the sample cannot be right or keep this angle if you are making these steps. Okay. And this part of the fourth sample will have or will lose this angle. And as we see in previous slides, if we change this angle, you need higher tensile stress to reach to that critical shear stress that you need for the slip. And this happening here, it becomes like this, so this angle is no more 45, so material start to increase, the curve start to increase and the slope will change. That is because of the way we are doing the test. If you have a machine that you can adjust the position of these fixtures, maybe you can continue deforming the material without doing this, okay? So we answered several questions by this or by now. Another question that you have to answer is, if we calculate the shear stress or tensile stress is needed to deform the material plastically by a slip is about 10,000 megapascal, why magnesium start to deform by just 1 megapascal in this condition? Yeah. Yeah. Before going to answer this question, another things I want to explain is equivalent slip systems. It means when we have more than one slip system in a material. In previous tests that we talked, it was magnesium and basal plane, that is the only plane inside of HCP, and all of them are parallel, that has a closed pack structure. So if you put that plane with the 45-degree toward the tensile test or tensile stress you are applying, yeah, so you can have just easy glide in this plane. But in the case of FCC, for example, now we explain that and we know that in FCC we have more than one slip system which are equivalent. We have 12 slip systems which are equivalent, and all of them are closed pack plane and closed pack direction. And you know that, for example, this. If you are applying load in this direction of a FCC crystal, it means these four planes and these directions all are equal, yeah, for the deformation or for a slip, yeah. So if you have a single crystal FCC and you are applying load in this direction, yeah, it means in this plane you have a slip, in this plane also you have a slip, in this plane and all these two other planes also you have a slip. It means several slip systems at the same time are activated, yeah. And what happens in this condition? Because for this condition, which is just magnesium, just in this direction we have a slip, so we can see here easy glide, and nothing happened because just these planes are slipping on each other. Nothing happened, just practically as we cannot adjust the fixtures of our equipment, we see this part is going up. But in the case of FCC, if you are applying load in this direction, imagine you have a sample like this, it's a single crystal FCC, and this direction is 1001. It means at the same time you are activating several slip systems together, okay? What will happen? So let's see. Here is the stress strain curves of the FCC crystal, single crystal FCC, yeah? And it depends on the direction you're applying load, yeah? Now just we are showing two directions, A and B, okay? A is close to the direction of 0, 0, 0, 0, 1. This is like a square is the direction of 0, 0, 1. This is the direction of 1, 1, 1. And this is the direction of 1, 1, 0, okay? They call this portion or part of the triangle of stratigraphic triangle, that is crystallography. I don't know if you know this triangle or not. Yeah, if you don't know, just ask me, I can explain it more. But it's nothing about just crystallography. If you want to say by this, stratigraphic will show in which direction we are applying load. For example, when I say A is here, it means we are applying load on the direction of 0, 0, 1, this direction. Yeah. If I am here, I am applying load in this direction, or if I am here in this direction. We are just comparing these two directions. It means one of them is close to 0, 0, 1, and another is the middle between these three. It means none of these directions, but in a condition that can activate just one sleep system, not several. Okay, so first let's talk about in this direction. It means this direction, yeah, where we activate several sleep systems together. You will see the shape of the stress strain curve is like this. Yeah, it means when we apply load at this stress, we reach to the plastic deformation, and from the beginning, the stress is needed to deform more is growing or is increasing. Yeah, why? We call it a strain hardening. Yeah, or a strain. It's more difficult to make a deformation when we do more strain. Yeah, this is the reason of this is why it's different than, for example, magnesium one is just we are applying when we are applying load in a direction that we activate several sleep systems, they interact with each other, and something happen inside of the material that more deformation is more difficult. Yeah, this is so bring us another question: what is happening inside of the material when we have several sleep systems are activated? Yeah. Comparing to this, if you apply load to this direction for FCC crystal, yeah, it means in this direction, just one sleep system is activated. So again, like magnesium, we see that easy glide part. Yeah, the deformation starts, material easily start to deform, and the stress is not raising because just we have deformation in one sleep system. But after a while, yeah, again it starts to increase. We come to the region of 2. Yeah, it means when we reach to this part, yeah, other sleep systems also become activated. Yeah, so a strain hardening again occurs in this material, this crystal, and when the stress reaches to this high amount like this, again this slope come down, and the reason for this is because at highest level of stress than like this, all systems, even those systems that are not activated in lower stress become activated, so the formation again become more easy than before. Yeah. So in FCC crystals, for single crystal, for a stress strain curve, we can see two type of curves. This curve is when several equivalent slip systems are activated, and we have strain hardening from the beginning. So far, we don't know why. I am going to explain it. But if we just manage to apply load in a direction that we can activate just one slip system, similar to HCP like magnesium, we can see the easy glide part. And after a while of deformation, we will see strain hardening. And again, we see decrease of that strain hardening. Okay? So we are going to see what is a strain hardening, why material have a strain hardening, and why from the beginning when we apply load deformation is very easy in materials. Yeah, deformation starts very easy, but for further deformation, we need further stress. It means a strain hardening. So two questions. What we have inside of the material, inside of the metal that help us to have very easy deformation, very easy plastic deformation, and why when we have this deformation to continue deforming the material, why we need higher stresses if we continue. Yeah. So these two questions are something we have to go inside of the material to see what we have inside. Theoretically, we calculate that if the mechanism is slip, with these other equations, we need very higher stress than that is practically is needed for sleeping or moving two planes together. Yeah. So let's go inside of the metal to see what we have inside that help us for plastic deformation. Okay. You know, to evaluate metallic material and to see the crystal structure and microstructure of the metals, we have different characterization methods. One of them is XRD or X-ray diffraction by applying X-ray on a metal and diffraction of these X-ray waves, we will see we can know the crystal. That's why we say this is FCC, this is BCC, this is ACP. Yeah. Another method that we can understand something about metals is we can cut it, we can polish the surface, yeah, and by putting this polished surface on the like acid, yeah, something corrosive, we can observe something, some defects, yeah. So you know, for example, if you do, we call it etching or attack chemical, yeah. When you do that, for example, you can see the grain boundaries. For example, this line is a grain boundary, okay? And you know the reason. Grain boundary is a place or is a defect inside of the metal that the energy of this part is higher than other parts. So when you put it in the acid, this part will be corroded more. So inside, beneath the microscope, we can see it as a line, okay, on the surface. When you do this etching for a metallic material, we can see this point too, something like this. You can see there are several. They are sometimes in a line. They are sometimes separated like this. What they are, yeah, and how they form. This, what is this shape? Yeah, this is just something like this. When you have a surface of the sample or metal polished, and when you put it in the acid, a pit, something like this, will form. Okay, and this is nothing but is a dislocation. Is another defect we see inside of the metallic material that come to the surface. When it's come to the surface, around this dislocation, we have higher energy than other parts of metal. So if it's around is a corrosive media like acid, so this will be corroded and a pit will form, okay, like this. And why is like a cubic or a square? Because this plane is 100, yeah, and when this is 100, this corrosion by acid happen like this because this plane, and this plane, and this plane are 111. And this 111, as are close packed, yeah, they are less, or they are more stable, so that acid can corrode them less. So by this way, you will form a pit like this. So under the microscope, you will see like this. So they are these each of these pits belongs to one dislocation. So these dislocations come to the surface, and the surface depend on the plane we have here. We can see these peaks, which are dislocations. This is in the case of 111. If this plane is 111 itself, these become like a triangle, become like this. Yeah, we call them HP. This is the first observation of dislocation that we can understand. We have more than grain boundaries, or inside of the single crystal, we have some defects. Yeah, we call them dislocation. Also, we can see them by electron microscopy. This is the observation of dislocation beneath the electron microscopy, and this is something like this. We make a foil. This is the case of aluminium. We can make a foil, and this AB, yeah, AABB is a part of the plane, a slip plane. Inside of this slip plane, we have dislocations. One line, two, three, four, five dislocation. But when you see it with electron microscopy, you are seeing two dimensions. It means you are seeing like this. So all of them are dislocations that we can see with electron microscopy. Yeah, this is a three-dimension that we see, but as we take photo, is we are seeing as a two-dimension like this. So this is like this. Okay. So inside of the material, we have some defects, which are dislocations, and these dislocations help us for plastic deformation, or help metallic material for plastic deformation. How? Like this. If you have dislocation, I don't go inside of definition of the dislocation, because I know all of you know about dislocation, so easily I can do it more fast here. So if you have dislocations in a metal, when you apply shear stress like this, yeah, you have a dislocation here. This is a dislocation, yeah. Instead of moving all these upper parts of this crystal together, it means you have to break all these bonds. Just you are moving this extra plane that you have, like movement of this caterpillar, yeah. So this, when you move like this, need less stress, yeah, less shear stress. So movement of dislocation inside of the metal help us for plastic deformation, and that is why metallic material deform plastically very easily, yeah, because we have dislocations inside of these metals, and these dislocations move easily with low stress needed for movement, okay? And also, you already know that we have two types of dislocation. This is a edge dislocation. Also, another type of dislocation we have is a screw dislocation, which is like this. Okay, so we have to be familiar with this topic, dislocations. And the reason is simple. By just knowing dislocation, we cannot explain. We can explain why we have low stress level for plastic deformation, but we cannot explain it for strain hardening. Okay, we reach to that critical shear stress. It means we reach to that stress level that can move a dislocation. That is okay. So the plastic deformation starts, but why for further deformation we need higher stress? What is the behind of the strain hardening? Yeah. So to answer this question, we have to know more details about dislocations. To talk about dislocations, you have to define them. Yeah, we define dislocation by Berger vectors and orientation. Yeah, and Berger vector is something easy. If, for example, if you have a perfect crystal without defect, without dislocation, if you start from one atom and you make a loop, you reach to this atom. Okay. But when you have a dislocation here, if you start from this atom, you will not reach to the origin. So this is a Berger vector. Yeah. And for a screw dislocation, also the same. If you have perfect crystal, you reach the original. But if you have a screw dislocation, you're not. And this is your Berger vector for a screw dislocation. Yeah. And here I mentioned also here is a brief explanation of what is S dislocation and what is the screw dislocation. Yeah. So the S dislocation lies perpendicular to the Disperger vector. It means if this is a dislocation, yeah, or Berger vectors is vertical to this line. Okay, this is the edge dislocation, and this edge dislocation can be positive edge dislocation and negative edge dislocation. If the movement is to this side, or extrapolane is down, or extrapolane is up, we classify them as a positive and negative edge dislocations. For screw dislocation, the dislocation lies parallel to the Berger vectors. Yeah, so it means if this is the line of dislocation, Berger vector also is in this direction. Yeah, and also we have, depend on the direction, we have left hand screw dislocation and right hand screw dislocation. So Berger vectors is something that we can talk about dislocation with this vector. Yeah, you know, when you have a dislocation in a metal, it means one part of the metal is slipped or is deformed. Other side of this dislocation so far is not slipped or is not deformed. So dislocation line all time divide crystal from what deformed part and undeformed part. And as it is, we cannot finish a dislocation line inside of the crystal. It means dislocation must reach to the surface or inside cannot be finished. Yeah. So inside of the metal, when we have dislocation that are not reaching to the surface of the metal, they must be like a loop, like this. Yeah. When you have loop, it means this part is deformed and around is not deformed. Yeah. And when you have loop, it means you have, if for example, Berger vectors is in this direction, okay, this is if this is the slip plane and this is the Berger vector of this dislocation. This dislocation in this part is edge, and in these parts is a screw dislocation. Yeah. So a loop, a dislocation loop, all time is consists of the screw and edge dislocation. Some part is dependent on the direction of the Berger's vector. Some this part is, for example, the screw, and this part is edge dislocation. Yeah. And this part is the mix of both. When we are transition, we have a transition from a screw to the edge. Okay. And we can show these Berger vectors by notation of crystallographic directions. A summary of these three important crystal or four important crystal structure in metallic materials. I'm showing the Berger vectors. For example, FCC. For FCC, do you remember this direction is that closed path direction for FCC. So this direction is the direction of Berger vectors. And the Berger vectors is distance between two equivalent position of atoms that, for example, for this is from here to here. So the notation for the Berger vectors of dislocation FCC become like this. This A0 easily can be written as a 1. Yeah. So, and for BCC, do you remember in the directional diagonal of this cubic is the closed pack direction. So the Berger vectors of the dislocation in BCC have this index, okay? And for SC is from this to this, so easily is this. And then HCP is this. They are notation of the Berger vectors in different crystals in metallic materials. They are just that. It's easily you can memorize them. And it's,
Teacher,
yeah.
um, I am a little confused because can we have a slip plane that moves, but not because of the dislocations, right?
No, all time is by dislocations.
Ah,
You
yeah.
know,
So
yeah,
at the first examples that you show in the class, from the slip planes, it is because of dislocations.
yes, yes. Look, let's
Yeah.
come back here.
Hmm.
We didn't talk about dislocation because we are talking about sleep and this shear stress. And here, the plastic mechanism is happening is sleep, and in a sleep plane, in a sleep direction. But as we have very low tensile stress needed for this sleep, and this is not is much less than that needed for moving all atoms. It means inside of this sleep system, which is a sleep plane, we have some defect that already we know is dislocation that are moving. Yeah.
Mm, yeah, but now I have another question because that is shear stress and the dislocation, you always show them with compression, like compression stress.
No, it's shear stress. It's not compression. Good.
Ah, yeah. Yeah, okay.
Also, if this is a shear stress, it means you are applying a stress for down part of this crystal in this direction, upper part in this direction. So exactly where we have dislocation, we have shear stress.
Yeah. Yeah.
Yeah,
Perfect.
it's not possible by compression or by tension move a dislocation.
Yeah.
Actually,
That
is possible, but the mechanism is not asleep.
okay.
We call it climb, yeah, and that happens when when we are in very high temperature, yeah. When we reach to the class, we are talking about creep. I will show you how a tension or compression can move a dislocation. But the mechanism is not asleep; it's something else. It's climb, we call it. Okay.
Okay.
And that
Thank
is
you.
because of the diffusion of atoms, not by a stress you are applying on the dislocation and the breaking the bonds. That is another history. Later we will talk about it. But we don't have movement of dislocation with compression and tension. It must happen by shear. And that's why we calculate that critical reserve shear stress that must have angle to the tensile test or tensile tension. Okay? Because it
Okay.
must be shear, not compression or tension. Okay?
Yeah. Perfect. Thanks.
Yeah. So we are here and we know the notation of the Berger vectors for dislocations in different metals. We have different dislocation with different notation in different direction because they are in different slip systems. Now let's talk about dislocation in FCC lattice like aluminum, silver, gold, those metals, copper, that easily we can deform them. Let's go inside of them to see what happens in these metals. And one question again raised is why, if we have pure aluminum and pure copper, both are FCC, But why we need different level of stress for deformation, movement of dislocation? This question I will explain in next class, but now let's see the details of the in general dislocations in FCCs. Okay, look, so this is FCC. It means this is a slip plane, and these directions, and these also, and these are a slip direction. So if we look from upward, we will see something like this. Okay. If we have a dislocation, it means we have something like this here. This is a dislocation here, this part. Okay. And when we apply shear stress on these planes, it means this is one plane that is a dark, and this is white balls or the upper plane. And by shear stress, we want to move this dislocation here. It means if these atoms we are showing by B are moving from this position to this position, this dislocation moves to this direction. This is the movement of dislocation inside of the FCC crystal. It means this dislocation with these Berger vectors is moving in this direction. Yeah. The same will be in HCP because this plane in HCP basal plane 0001 is similar packed, close packed structure than FCC. The only difference between HCP and FCC, this is a stacking. Look, I can stack these planes like this, A, B, A, B. It means if I put one atom here, this is A, this position is B. Yeah. Another plane, when if I put the same as A, become A, B, A, B like this. A, B, A, B, A like this. So this is ACP. But we can put like this, A, B, C, A, B, C. It means this is the B, yeah, okay. In top of this, I can put this again here on this, so will be A, B, A, B. It means from here, for example. Here we have 6 hole. Yes, when we have just one plane. 6, okay? When you put another plane on this, become 3, like this. 1, 2, 3, yeah? If I put the third plane just on the top of the A, this all time become open, will be open, yeah, these 3. That is the situation in A, B, A, B. So in A, B, A, B, all time we have these 3 holes open. But if I put in C, I will close this. Yeah, you will see this will be closed. This is the difference between HCP and FCC crystal. Okay, keep this in your mind. This stacking of the planes, especially for FCC and HCP. But here, look at this. This dislocation, if you are applying a stress like this, so you are moving this dislocation to this direction, and these atoms become here. Okay, so this atom must go up and come down. It means in front of this atom is like a barrier. This atom is a barrier for this is for this, and this is for this, like this. Okay, imagine if you have an atom here, this atom here, it means yeah, is drawn here, small one to see the net. Okay, must move from this position in the crystal to this part. Okay, imagine instead of going directly from this position to this position, if it's come here first, after that go there. This is more easier. This all time is just passing in a lower part of this crystal plane. Yeah, no need to go up and go down, and need less stress, or is less energy to move to this. Yeah, it means if you do like this, now you have two dislocations here. This is one, and this is another one. If this move here, it means this dislocation from this position came to this position. But when you make such a situation, it means dislocation movement is not completed. It's a partial dislocation. It means this dislocation is decomposed in two partial dislocations. Yeah, this is one, and this is another. This is the Berger vectors of these partial dislocations. So the composition of the one dislocation in two partial dislocation help the formation in FCC crystals like this. Okay, right? It's clear.
Yes.
So when you do that, yeah, you are making a stacking fault. Do you remember what is the stacking? It means A, B, C, A, B, C, A, B, C. But if you do like this, or this dislocation, the composition happen, you have A, B, C, A, yeah, must have A, B, C again. Here, by this, the composition of dislocation, you have A, B, C, A, C, A. It means a part of this dislocation convert to ACP. That we call it a static fault. Okay? To be familiar with this, it's like this. Look, when you have a partial dislocation, it means that this dislocation decomposes in two dislocations. Yeah, these two dislocations are, we call them partial dislocation. In the case of the FCC lattice, they call them Shockley partial dislocations, and these very easily happen in FCC metal and help material to deform more easily. Yeah, you will see the position of these atoms compared with this is in a C position, no in B position. So if you have here A, B, CA, here you have CAC. So here we call it a stacking fault. Okay, and if it's happening or not. Okay, if this is happening, but energetically is happening or not, or this is when this the composition of dislocation happens, the energy of the system increase or decrease. Yeah. To answer this question, because if the energy of the system increase, it's not possible to do such a decomposition. Yeah. You have to know about the energy of the dislocations. Okay. This is about a strain energy of the dislocation or elastic strain energy of dislocation. You know, when you have a dislocation inside of the metal like this, let's come back to schematic. This is a problem when you don't have white words and you cannot draw whatever you want. Okay. Look, here we have a dislocation, yeah? This is a positive dislocation here. This is the core of this dislocation, yeah? It means we have an extra plane here, and here we don't have. So the bones beneath this dislocation are under tension, and here under compression. So in these parts, around up, we have compression strain. In the down, we have tension, yeah? And this tension is something has related to the distance, how much we are far from dislocation. So in general, around the dislocation, we have a stored energy, elastic energy or strain energy, okay? We can calculate this energy, and this is this energy of dislocation. You can calculate the energy of the edge dislocation. This is the formula, and this is the screw dislocation, and this is the formula. I'm not going into details of how we can calculate. You can find it in the reference books I presented. So you can see the details, but something for us is very important and is easy to use it is the energy of the dislocation has relation with a square of the Berger vectors. Yeah. So if you calculate the B2 for each dislocation, you can relate it with the strain energy of dislocation. So when we have this decomposition, you have to calculate this B2 for this, and this B1, 2, B2, 2, yeah. If the sum of these two is less than this decomposition can happen easily. And this is like exactly, this is true. Then you can calculate it, yeah. Also, it can be a question for you. We have lots of partial dislocations that you can evaluate if these partial dislocations or this dislocation can decompose to these two partial dislocations or not. If this equation is become positive, so it's not positive. If it's negative, it means it's positive. Okay? So here we have two partial dislocation in FCC crystal that make a stacking fault, and the schematic is like this. You know, these two partial dislocation are separated. How many atoms or how many planes are between these two partials? Yeah, it means this is when they compose can be like this, very narrow, or can be like this. Yeah, this is depend on two factors, and for different metals is different. Yeah, the one factor is that repulsive energy that this dislocation have. They want to escape from each other. So we have a repulsive force between these two partial dislocations that separate them from each other. Another factor is playing here is surface energy. It means this is a fault, this is a defect inside of the metal. So increase the surface energy or energy of this plate there. So the balance of these two energy, it means a stacking fault energy and repulsive energy of the two dislocations can define how much these two partial dislocation can be separated and how much can be close to each other. And this will affect the behavior of the material or metal because in some conditions they must come together and make a dislocation or compose to make a dislocation to help the formation continues. Yeah. If they are too separated, for example, is more difficult. So this when we have different metals, FCC metals, as this energy and this repulsive energy is different, so the behavior of different metals also is different. Okay. Now we just learned about the shortly partial dislocation in FCC metals that help the formation, but we have also another type of partial dislocations in FCC metals. These shortly partial dislocations that already we talk about it and we see it in FCC, we call it glycide dislocations. It means they can move and help the formation of the metal. Yeah. Other type of the partial dislocation that we have, we call it frank partial dislocations. Schematic is like this. When you have a dislocation here, and this is the S dislocation, and the Berger vectors is perpendicular to this slide. It means when you have in this direction, Berger vectors is not inside of the slip plane. Yeah. So this dislocation, this partial dislocation cannot move. Yeah. If you have such a partial dislocation inside of the metal, we call it sessile dislocation. And another name is the quadrilemma barriers. Yeah. So not necessarily all dislocation can move. You see sometimes dislocation decompose to the partial dislocation that are sessile dislocation. They cannot move. Yeah. Another things happens inside of the metals like FCC. You know, FCC, I told 12 slip system we have. For example, we have 4 slip plane, they make angle with each other like this, okay? If we have dislocation in this plane and we have dislocation in this plane and both are activated or moving, in some places they come to have intersection, yeah? So dislocation when intersect with each other, yeah, they cannot cut each other. So they cannot, for example, this if this is a dislocation loop inside of a metal and one dislocation from another plane is coming here and when they intersect, these steps will form. And we cannot cut this loop because we cannot end a dislocation inside of the metal. So this cutting or these steps can be in 2 conditions. One, we call it kink. They are kink. Kink means this step that is formed lies in the slip plane of the dislocation, is inside of the slip plane. It means this is the plane and this step on the dislocation is inside of the slip plane. Can be edge or can be a screw, depending on the direction of the Berger vectors. You'll see. Elimination of this kind of kink is very easy. Just if this dislocation move, this step will be eliminated. Yeah. Another type of steps can form is jog. We call it jog. Yeah. When the step is not inside of the plane, the slip plane of the step is different than the slip plane. Like this. You'll see, the slip plane was this or is this, but this dislocation is here. It means that the slip plane is different. Yeah. In this condition, if, for example, in this case, if you are applying a stress in this direction, this dislocation move, this jog also move because the Berger vectors is inside of this slip plane, so can move. It's not a sessile, okay? But in this condition, like this, the Berger vectors of this edge, yeah, is in this direction, and the slip plane is this, so is vertical to the slip plane. So this part of dislocation or this jog is sessile. It means this part of dislocation cannot move. Yeah. So sometimes when dislocations intersect, they can make sessile jogs, and part of this dislocation is like being locked. Yeah. And when they become locked, the movement of dislocation is difficult. This is one reason for a strain hardening, because when you active several slip systems, obviously this dislocation intersect each other. And when they intersect each other, they can make this kind of lock. Yeah. So the dislocation movement will be more difficult after. So from that stress strain curve of FCC, that at the beginning we have a strain hardening. The one reason is because we have several slip system activated, so dislocation easily cross each other. They make such a locks, and the movement is more difficult. The deformation is more difficult, and that's we call it strain hardening. Okay, this is one reason. Yeah. Another thing, Before explaining this, you know, even in very or full annealed metal, we have dislocation. It's very difficult to have a metal without dislocation. Yeah, and we quantified the quantity of dislocations by density. Later I will explain it, but here I want to make a question that help you to understand this slide. If, for example, we have a certain quantity of dislocation in a metal and we start to deform it, obviously some of these dislocations which are inside of the metal come to the surface and they escape. So the density must decrease after deformation, not increase. Yeah, because finally, or if you have positive dislocation and negative dislocations, if they come to each other, they can cancel each other. So this is elimination of dislocation. So the density of dislocation must decrease by plastic deformation, not increase. But actually, we see in metals, when we deform a metal, the quantity of the dislocation raise. It means, for example, if you have 10, I don't know, 10 square 6 dislocation per square centimeter, this will reach to 10 times 14, something like that, okay? It means the quantity of dislocation increased. So we have some source for generating more dislocation, for making more dislocation by plastic deformation, yeah? So what is that? Why dislocations are made during the plastic deformation, yeah? Let's see. Look, if you have an FCC crystal, it means, for example, this plane. Inside of this plane, you have a loop like this. So this loop, the Berger vectors, for example, is in this direction. This is S dislocation, negative. This is positive S dislocation. Here you have a screw dislocation, left hand and right hand. Okay. When you apply shear stress, all of them start to move. Yeah. This screw dislocation move to that direction. This is to this direction. This is to this direction, and this is to this direction, and this loop expand. Okay, like this. Okay. But you will see we have 4 similar planes inside of the FCC that make angle. For example, this plane that we are talking about has angle with this plane, like this. It means this is another plane, equivalent plane inside of the crystal, yeah? So this dislocation, if it can move inside of the plane, if it's coming here, why it cannot cross a slip to another plane? This also can happen, yeah? So this dislocation can change the slip plane from this plane to this plane. That we call it cross slip, yeah? But something happened. When this happened, when this dislocation comes to another plane, which has angle with original plane, yeah, not necessarily all these Berger vectors remain. Just Berger vectors of screw dislocations remain in the plane of a slip plane. Okay, it means this portion and this portion, yeah. Sorry, we are talking about this because this is another photo or schematic here. Here we have a screw dislocation. Also here we have a screw. Here we have edge, and here we have edge. Why? Because Berger vectors is in this direction. Okay. So when this loop come cross to this plane, these two parts, which are screw dislocations, again, they have the Berger vectors inside of the plane, so they can move again. Yeah, but in this part, here you can see this part and this part of dislocation, which is edge dislocation, the Berger vectors is not inside of this plane, so cannot move. So when this loop cross to another slip system, a slip plane, just a screw portion of this loop can move. The edge parts cannot move. It become like this, just lines. Yeah. Again, they can move to another plane or to come back to original plane, another plane parallel to original plane. When they came here, again, they become inside of the similar plane, so both part of the screw part and edge part can move and become expanded. Okay, that we call it double cross slip. Yeah, and this very is happening very frequently in FCC metals. This cross slip. Okay, so don't forget what we are talking about. We want to talk about why the density of dislocation increase with plastic deformation. Okay, just remember this plane. If I, for example, continue like this, yeah, this is a plane of forget down what is happening. So I just shift it here. We have 2 points here. A dislocation come out. So is it moving? If you continue, it move like this. Yeah, can expand in all directions. Okay, so these 2 points are here. This it means this plane is that plane that dislocation can move. Edge dislocation and screw dislocation both can move, but these 2 points cannot move. This dislocation, this line of dislocation, which is coming from another plane, exactly in these 2 points cannot move. Why? Because if it's moved, it means you are moving this part also in this plane. It's not possible because this plane doesn't allow this dislocation move. So we have here 1 point, and here we have 1 point. That dislocation in this place is locked. Okay. So when you have dislocation like this and is locked in these 2 points, when you are applying a stress, dislocation again start to expand. But this expansion is become like this because it's locked in these 2 points. It's continue expanding, expanding to finally this part and this part come together, and this part is positive, this part is negative, so they cancel each other. When they cancel each other, you make a loop again, a new loop. It means a new dislocation or burn or generated. Okay. Again, here you have a line. If this stress continue, again, this can do the same. Yeah. Another loop you can form. Another loop you can form. And this, we call it Frank-Reed source. A Frank-Reed source of dislocation. It means by plastic deformation, by having such sources, we are generating more dislocations. That's why the concentration of dislocations by plastic deformation is increased. It's clear?
Yes.
Good. So I think now we can understand easily this stress strain curve for for example, a metal. Yeah, we can divide it in 3 stages: easy glide, strain hardening, and again the third stage that again deformation is easy. Yeah. So now you know this critical resolve shear stress that we calculate by this equation, and how this is related to the direction of the sleeve system and the tensile stress that you're applying, that already we talked about, that 45 degree. And if you have deformation in just one slip system, you have this easy glide part, yeah. But after deformation, and because we activate more slip systems, yeah, so a strength hardening starts, become like this, okay? And this strength hardening increase the stress, that the level of the stress reach to a point that can activate other sleep systems that are more difficult to become activated. So again, this slope decrease. Okay, so you understand all these parts by this explanation we did so far. Okay. So this is just extra explanation for this. You can easily read it later. Yeah, that's you're explaining the stage 2. That is barriers, low structural barriers. Yeah, is for increasing the strain is needed more stress. Yeah, and the strength hardening is happening. Yeah, and cross slips that happens inside of the metals. That was FCC. In HCP also we have the same, as this basal plane has a similar configuration. Deformation also can happen by partial dislocations, and this the composition of the dislocation for HCP is like this, becoming two partial dislocation. The same also you can calculate the energy of each dislocation and understand that this sum of these two is less than this, so this decomposition can happen easily. This ACP dislocation, they don't have much more that we can talk about. Yeah, and dislocation sources also we talk about. Now you understand why we report the density of dislocations, yeah, by square centimeter, because you can count it on the surface of that sample. For example, this is the annealed one, and the number of dislocations we can count in an area, so that the dislocation density becomes the number of dislocations per square centimeter. Okay, and when metal is annealed, this density is about this quantity, but when you do cold working, we are increasing the density of dislocations by, as I explained, by activating some source of, like a front grid source for generating more dislocations. Okay. In some metals is not easy, just we call it whiskers. Whiskers are very tiny metals that we can fabricate by melt spinning or some special method like from vapor phases. That type of metals can be dislocation free, or they don't have dislocations. Yeah. Other metals like the common manufacturing processes, all they have dislocations from the solidification, and we cannot avoid these dislocations in metallic materials. In all, we have dislocations. Okay. So that was, I want to talk about dislocation today. We are not finished with dislocation and plastic deformation of metallic materials. And if I continue, I think you will be confused and will be tired. So I stop here. Later in next class, we continue talking about dislocations, and we talk about dislocation in ceramic materials. We can talk about dislocation in covalent materials, and the Here's first force that's need for movement of dislocation, and talking about if dislocation exists in ceramic material, why ceramic material before the movement of dislocation they break, or in covalent materials why they break. Yeah, and it's something related to the stress level that material reach to be fractured. Yeah, if another stress level is a stress level to move a dislocation. If you reach to that level is needed for fracture before moving the dislocation, material will break. If you reach to that level sooner, so material will deform. In metallic materials, before reaching to the level of fracture, we reach to the yield point. It means movement of dislocation. That's what they are ductile. We have plastic deformation. But in other metals like ceramics, for example, covalents, this stress is needed to move a dislocation is so high that before reaching to that level, material will break. Yeah, this we will talk about it next class and more in detail when we talk about fracture. Yeah, I hope you enjoyed this class. If you have questions, let me know.
Sir, uh, in general applications, we don't have like a single crystal, or don't we? Like, for example, in engineering, we don't have a metal in a single crystal, or
Yes, we
do?
have in several applications. We have to make single crystals. Yeah.
Ah, okay.
For
Okay.
example, one simple one that also I explained is about turbine blades. Okay, turbine blades to have
Ah,
you can solidify that turbines just having one nuclei, and this nuclei just is limited and is directional solidification, so turbine can be a single crystal. Making a single crystal is not difficult and doesn't have relation with this topic because inside of single crystal also we have dislocation.
okay. I thought that a single crystal was like an application only in labs or something like that,
No, no,
or
no.
experiments.
We can make a single crystals and it's not actually too difficult to make a single crystal.
Ah, okay. Thanks.
More questions?